Alright, today we're gonna learn about mechanical properties of metals. So we know metal parts, they are exposed to forces, and how they react to those forces determines their mechanical properties. So when a metal is exposed to mechanical forces, what parameters are used to express force magnitude and degree of deformation? So based on how much force it was applied, how much it will deform, or when it will fracture, when it will fail. So those questions we're going to answer. And some of you might have familiar with these topics because I'm sure you have seen these in other classes maybe. And we're going to see the difference between elastic and plastic deformation. What is elastic deformation? What is plastic deformation? So how are the mechanical properties are measured? So we're going to see different types of tests that are used experimentally to determine the mechanical properties of materials. And I suggest you guys also watch the videos that I provide, because all those videos will show you how those tests are done. If you are interested, you can also watch those. So when we say mechanical properties, these are stiffness, strength, ductility, and hardness. And how are all those measured? Okay, so different types of tests are being used to measure these properties. So which parameters are actually used to quantify these? So when we say ductility, which parameter we are going to using to say the material is ductile or not? So what are common states of stress? What type of stresses basically the materials are exposed to? And the most common one we call tension or tensile stress, and we show it with sigma. You can see a part here which is exposed to forces, uniaxial forces, meaning along one direction, like we are pulling the material from both directions. So the material we say is exposed to tensile stresses. So the cross-sectional area of that bar is A naught, okay, or the cable is A naught. Of course, the cross-sectional area will change as we keep applying the load, like it's gonna get smaller and smaller, but the initial is A naught. Okay, this initial starting cross-sectional area is A naught. So how do we define the stress? This is like pressure, right? So stress is force over original cross-sectional area. Another type of stress is torsion or shear, okay, where there's a drive shaft, for example. The material is exposed to torsion, like twisting. As you see here, we are trying to twist the material on both sides, and there is the torsion moment. Here we are seeing torques, and the cross-sectional area is 2r. The cross-sectional diameter is 2r. The cross-sectional area is AC, okay? And AC is the original cross-sectional area. So the shear stress here is defined as, again, the force over area. If we look at the small unit within this shaft, or you can write it as, instead of force, you can say moment over the radius, and with the original cross-sectional area. There is also compression stresses, right? When we are trying to compress a material. The formula is the same as the tension. Basically, force over area defines the stress. And many different parts are exposed to compression, like parts that we use in bridges, rocks, etc. Pressure tanks are exposed to basically biaxial tension. Basically, tension happens in two directions, transverse directions. And when we look at the pressure, it is pressed in every direction, right? So we call that hydrostatic compression. In 3D, in all directions, there is stresses on the animal. So those were examples of different types of stresses the materials are exposed to. And the most important one is the tension. And how do we measure how the material is reacting towards a tensile stresses? We have tension tests we perform to be able to determine the properties. And to perform this testing, we call it also stress strain testing. We need a specimen, and specimen needs to be prepared in this shape where there is reduced cross section, and we measure a gauge length where the gauge length is where the deformation will be observed, and that specimen is fitted in the device. The device will pull basically the part uniaxially in both directions. Okay, so specimen is placed. There is extensometer, which is a sensor detecting the deformation, because when we actually pull the material on both directions, the material will start to get longer, right? Extend or deform, or we call it strain. It's gonna change dimensions, and then extensometer is able to measure that change. So in this test, what happens is the machine applies a constant deformation rate, meaning every second, let's say, I'm going to make it up, okay, every second it is trying to deform the material, let's say 10 millimeter. Okay, I'm making that, okay. So basically the deformation rate, the device is trying to keep that constant, okay. And what it does is it records the force that it needs to apply to keep that deformation rate constant. So with time, of course, the force will change as the material keep deforming. Less forces might be necessary to deform because it will deform more easily. So what I'm trying to say, it will keep the deformation rate constant, but measure the forces, measure the deformation, and then calculate the stress and strain from the equations we're gonna learn. So what type of stresses the materials are exposed to? We said the tensile stress, which was the sigma, which was force over original cross-sectional area. and the shear stresses are acting along the surface like that, trying to shear, and the shear stress is also force over the cross-sectional area it is acting. When we define strain, engineering strain is shown with an epsilon subscript z, meaning the deformation is happening along the z direction. But actually, when the deformation happens at z direction, let's say this one we have here, right? And no, not this one. Okay, so originally, let's say we have this one, right? And then we pull this, and when we pull the mid part, it's going to elongate, but when it's elongating in z direction, in the lateral direction, it will be exposed to acting like it is compressed. It will get smaller. Okay, so therefore, if you're going to define the deformation, you need to be careful in which direction you are defining that. So in this case, strain or the deformation with tension along the z direction is shown with epsilon subscript z, which is equal to the change in the length, which means the final length minus the original length, over the original length. Okay, so this is showing us the strain. And if you're going to define the lateral strain, which is the deformation in the transverse direction, that is the change in d. So this dimension is like maybe diameter, right? So shown with a d. So delta d over d naught. So delta d is final diameter, let's say, minus original one over the original one. So this is a deformation strain along the x-axis. But when we usually define engineering strain, it is the one that is along the z direction. Of course, shear stresses will also cause deformation in the material. Just like here, if we expose the material to shear stresses, the material will deform like this, right? So it will make an angle compared to the original starting point here, theta. So the tangent theta is actually how we define with the gamma the shear strain, shear deformation. That is delta x over y. All strains are dimensionless because at the end we are dividing length to length or diameter to diameter. So the units cancel. So when we say strain is something dimensionless. So materials deform elastically and plastically. So the elastic deformation is the deformation. So when we release the forces, the material can go back to its original shape. So it is reversible and you can recover it. So when the material is deforming elastically, there is a relationship between the stress and strain. Strain and stress are proportional, and the proportionality constant is defined by elastic modulus or Young's modulus. We showed with a symbol E. Okay, so this Young's modulus or elastic modulus is the property of a material, basically comes from the atomic bond strength. Okay, so if material resists to elastic deformation, it means it has large elastic modulus or Young's modulus. It means the atomic bonding is strong, and we saw that parameter when we were looking at atomic bonding. We briefly mentioned, and so this linear relationship between the stress and strain is defined with the modulus is equal to stress over strain. and or strain is equal to stress over modulus. Okay. So because when they collect the data from the tension test, and they measure the force at the device, and from the force they divide it into cross-sectional area and the test equipment, giving us this curve. We call this stress strain curve, and then on the y-axis we have stress, on the x-axis we have strain. Okay, and when initially always the material deforms elastically, that means a recoverable deformation, there is a linear relationship, the material behaves like that. Okay, so stress and strain proportional, and the proportionality constant is E, or this is also the slope of the strain stress curve. Okay, so when we understand Young's modulus and the origins of it, I told you guys atomic bonding. If we say material is stiff, that means the material has a high modulus. Okay, stiffness. And if it's like a rubber, for example, easily deform to a large extent elastically, then the Young's modulus is low. So for example, for metal, ceramics, the Young's modulus is high. For polymers like rubber, the modulus is low. It can easily deform. Okay, so how do we obtain some correlation between these equations? So we said strain is stress over modulus, E, Young's modulus. And then this is also equal to, we learned strain is delta L over L naught. Okay, so I come to here. So I know this. I know the stress is stress. Instead of this stress, I can write force over cross-sectional area, and there is E, which is equal to delta L over L naught. So this gives us delta L as force times L naught over area times Young's modulus. Okay, so this is that equation here, which tells you, besides the force and the Young's modulus, beside the force and Young's modulus, the geometric parameters will determine the deformation, because delta L is telling how much the length change, like the deformation, right? So we see that from this equation also. Okay, so let's erase everything on the screen and look at the second equation here. So there is a property called Poisson's ratio. We show it with a symbol V. This is by definition, the Poisson's ratio V in this equation we are seeing is equal to the lateral strain over the z direction strain. Okay, and there is a minus sign. The reason is when we elongate the sample in the z direction, remember it is compressed in the x direction, in the lateral direction, so it is actually, there is a negative change in the strain is actually negative because it's not elongating, it is short, it's under compression, right? It's contracting. So this is negative. With this negative, it is the making Poisson's ratio positive. Okay, so by definition, we said Poisson's ratio is LAX, the epsilon x over epsilon y, or epsilon y over, epsilon z. This is z. Okay. So the lateral deformation, the delta D, we defined it along the x-axis. We said, remember, epsilon x is equal to minus delta d over d naught. So this is Poisson's ratio, how it was defined. And instead of epsilon x, I can write delta d over d naught. So the negative sign here is again to make strain positive, because delta d is going to be negative, and we already accounted for that by putting minus in the Poisson's ratio. And this one is delta L over L naught. Okay, so instead of delta L, we can write this impression here. F times L naught over E over A naught. Okay, so let me write it again. Let's go here. So with that, L naught is gone. If we solve this for delta D, it should give us minus V F times D naught over F times D naught over E times A naught, right? So that is this equation here. So basically it again shows you lateral dimensional change is depending on the forces. Besides forces, the dimensions of the basically the material. Okay, so we learned here what is Poisson's ratio, and do you guys know a material with a Poisson's ratio of 0? That is gonna be cork. And cork has Poisson's ratio of 0. That means in the lateral direction, even now if you apply torsion in the transverse direction, it doesn't deform. The deformation is 0. That's why you are easily able to push it from the bottle top, because when you push it, it doesn't change the directions on the lateral dimension. If it does, it would be hard for us to be able to push and close the bottle. Okay, so that's it with this slide. There is also another useful relationship to explain torsion, which is angle of twist, that is related to the torsion strain. So this bar is exposed to torsion, right? We are trying to twist it, and if there is let's say we put a sign here like that, okay, and we cross the sample like that, and then if we try to twist, that line will come here. So there is the angle in between called the angle of twist, and that shows us how much the material is deformed. And this relationship is given to us here, but I'm not going to ask anything about torsion. Just giving you this information so that you guys can keep it in mind in case in the future you might want to use it and come back. You can see this equation here, which the angle of twist is basically related to the deformation, and that deformation is again related to the moment, dimensions, and G. So here all we understand from this chart, the important point we gotta understand again, the deformation is related to the forces applied, and then the characteristics of the material, and then the dimensions. And the characteristics of the material previously shown with Young's modulus when we were working with tension. But in torsion, when there's twisting, we talk about G. G is basically shear modulus. Okay, so let me write it down. So shear modulus shear modulus can come in the exam. Okay, this part is important. So how we relate shear strain to shear stress is with the shear modulus. So normally when we have tension, it was stress. Normal stress was equal to modulus and normal strain. So in that case, these are the same things, but instead of Young's modulus here, we have shear modulus, because this modulus is related to the shear. So that's why we use it with a G. We symbolize it with G. Okay, so G is important. And of course, this is again a linear relationship explaining elastic deformation under torsion, and the explaining relationship between the shear strain and shear stress. Alright, so we said elastic deformation is not permanent and reversible. Think about you have a rubber band and you stretch it, and when you release it, it goes back to its original shape, right? So this is what we call elastic deformation, and this happens at small deformations. Okay, so at large deformations, when you release the forces, you might not be able to go back to the original shape, such as let's say you have an aluminum foil, you bend it, and when you release the forces, it doesn't go back to its original shape, right? So when we are talking about small deformations, usually this is called elastic deformation, and it is not permanent, and the relationship between stress and strain is linear. As you can see, here is a graph of stress versus strain, and I showed you guys that under tension this is a linear increase, how stress is increasing with increasing deformation. Okay, so device was measuring force and was dividing into area and calculating the strain, and also measuring the deformation and calculating the strain. This was stress, this is strain. Okay, it's confused. Okay, so the slope was gonna give you the modulus, right? E. And okay, and when there is a linear relationship, E is constant, you can see, guys. Okay, E is constant throughout this deformation, and this is called Young's modulus or modulus of elasticity, and the linear relationship is called Hooke's law, that relates the stress to strain, and I showed you this one, guys. So what is the unit of modulus? Because this one is unitless, the unit of stress and unit of the modulus is the same, which is gigapascal or pascal, basically like pressure, right? So you guys need to understand, as I told you, the Young's modulus is a characteristic, is a property of the material, and it will change depending on what type of material you have. It is because of it is originating from the bonding, atomic bonding between the atoms, the strength of it. Therefore, we look at it, the highest modulus materials are ceramics, graphite, semiconductors, because these materials shown with the blue here, they have like diamond, very strong materials. Ceramics, they have ionic and covalent bonding, and this, of course, it is very difficult to deform those materials elastically, right? Think about, you are trying to stretch diamond, how possible is that? And then that means they are very stiff materials, so the modulus for those are very high. And besides that, also the metals are also the metallic bonding, providing other relatively high compared to polymers and some composites, higher modulus values. So we can see tungsten has the highest, because I told you guys tungsten has covalent bonding besides the ionic bonding, besides the metallic bonding. So it follows, the molybdenum follows it, steel, platinum, copper, and you can see tin and magnesium are the ones that have the lowest modulus. That means they are easy to deform, like aluminum, right? Aluminum easy to deform. You can easily deform an aluminum foil and aluminum bar. Okay, so when it comes to polymers in between the carbon chains, carbon bond is very strong, we know. But when we deform polymers, so remember this is one chain, another chain of polymers. In between them there is strong carbon bond. But between the chains, not within the chain, but in between these chains, we have weak bonds. So when we try to deform the material, actually these weak bonds are broken, not the carbon bonds. That's why you might expect polymers, because of these carbon bonds, to have a very high modulus, but in reality they have the lowest modulus compared to other materials, because of these weak bonds are determining the mechanical properties of polymers. So the chains can easily flow over each other, the material can easily deform. Okay, so composites and mixture of two different materials, they are mostly made up of polymer with the reinforcing fibers. Therefore, it is close, the modulus values are close to polymers. And of course, it covers a wide range, because composite means materials that are made by combining two or more materials. So they can put fibers into polymer matrix, etc. And this gives us a wide range of Young's modulus values. So this comparison between the moduluses of different materials, it's important. So this tells you again where the elastic Young's modulus originates. It originates from atomic strength. So how atoms change is displaced by application of loads, and if we remove the load, what happens? So you can see that initially, number 1, the atoms are well packed, and in number 2 we apply the tensile force, trying to stretch the material. Therefore, you are stretching the bonds. Atoms start to separate. Always, I think about when I think about the modulus or bonding between the atoms. Think about them like there's a spring in between them, and when you stretch this bond, it's like spring is extending, right? So in number 3, when we release the load or unload, the atoms can move back to their original shape. Think about you stretched spring and release the forces, it goes back to its original shape, right? And this was reversible, as we said. Okay. So most materials show a linear elastic deformation like that. When you deform it, you deform like this. There's this relationship between the force and the change. Of course, these can be converted to stress and strain. But some materials like polymers show non-linear elastic behavior. But at the end, it's elastic and it can go back to its original shape. Okay? This is like rubber behavior here. So mechanical properties of polymers, it's a little bit complex compared to metals, how metals behave. So as I told you, the modulus depends on the interatomic bonding forces or strength, right? and it is proportional to the slope of interatomic force versus interatomic separation. So logically you can understand that, right? How much you can separate the atoms with the applied forces. Basically it's gonna depend on the modulus. So basically if you have this force versus separation curve, the slope at the equilibrium separation distance is gonna give you is because you need it at that point, right? At a point, the slope is gonna give you the modulus. Okay. So the strongly bonded ones will have a bigger slope. Weakly bonded ones will have a smaller slope and smaller modulus, therefore. So this is, as I explained, the Poisson's ratio, and it is again dimensionless. But here I think they made a mistake, because this should be right. But also it basically depends on, of course, how you define the YZ x-axis basically. But it should be the ratio of lateral deformation to the deformation along the tension. So we are given the general values for Poisson's ratios, and this is for most metals, ceramics and polymers. It's in between 0.15 and 0.5. This is, as I explained, is the shear modulus, and this is obtained from the shear stress versus shear strain curve with the torsion test. And this G is again the proportionality constant between shear stress and shear strain. There is also one more modulus, and this is the modulus we called bulk modulus K, and this is when the part is exposed to hydrostatic pressure in all axes. It is under compression, and in this case P is the applied stresses again, and the deformation, the strain is overall volume is changing, right? So delta V over V naught, the volume. Delta V change in the volume over the original volume. And if you record this change for a part that is under hydrostatic pressure, the slope is gonna give you K. So it's the bulk modulus. All these modulus values depend on atomic bonding strength, and all these are actually called Hooke's law, because it is providing us linear relationship between stress and strain. And besides that, we can correlate the moduluses to each other. So if you want to figure out one modulus, but you know the other one, you can use the equations that correlate those moduluses, such as we can find from E what is the G, from E we can find what is the K. To be able to do that, but you need the Poisson's ratio. Okay, so we learned about elastic deformation, now plastic deformation. So plastic deformation is permanent. Okay, and so initially the atoms are in place like number 1, and when we apply the load, what happens is first it is elastically deformed, then there is permanent change in the atoms will slide over each other, atomic layers will slide over each other, and this is gonna be the plastic part of the deformation. And when you unload it, you will recover the elastic portion, but there is gonna be some plastic deformation is gonna remain. So the part is elongated. You cannot go back to its original shape in number 3. You see when you unload it, still a deformation remains, and it is called plastic deformation. So plastic deformation is, as I said, permanent and non-recoverable, right? So you can see here the force and this change in shape. You can see the linear elastic region here, and then the plastic is non-linear. You see now how force and change in the length is related. It's not a linear relationship, it's non-linear. And at some point, when you remove the stress, you go back to a deformation which remains in the structure, and this much delta L remain in the structure, but this part, the recovered, the elastic part, the linear elastic part, is recovered. So normally your deformation is this much, but this much is recovered, okay, and this much is remained. The delta L plastic is remained in the structure. So this is called plastic or permanent deformation. This again summarizes the stress strain curve, okay? So the machine records the force and change in length and converts them to stress using the equations we learned, and strain, and then gives us stress strain curve. It measures the force that needs to apply to keep the deformation rate constant, and then gives us the stress strain curve. And in elastic region, it is recoverable because it's just we are stretching the bonds between the atoms, and when we relieve the stresses, it go back to its original position, right? It goes back. But after some point is reached, the plastic deformation will start, meaning the layers of atoms slide over each other. And later we're gonna see this is gonna be certain atomic regions, certain atomic planes that has required the lowest amount of energy to move. Those are the ones that are sliding initially over each other, and dislocations are helping it. So by the motion of dislocations, the material is deforming plastically. So the material will keep deforming elastically together with the plastic deformation. So there will be a region where there is both elastic and plastic deformation going on. So from a linear region, we go to a non-linear region. And when we remove the stress, we recover some elastic, and the plastic strain remains. So this is just this is what the data is collected, but this is what the equipment gives us, converts to stress to strain using the relationships we learned. So when there is a transition from elastic to plastic deformation, this can happen in some materials like aluminum gradually. It cannot be an obvious change from sudden elastic to plastic, and there has to be a way to figure out from the stress strain curve to determine the yield strength of the material. Yield strength is basically the stress where the plastic deformation noticeably starts. Okay, and in design you never want to go over the yield strength of a material, because whenever you go over the stress values that is exceeding the yield strength of the material, basically the part is gonna undergo plastic deformation, and then basically material fails to serve us its purpose. So to get an information about what is the yield strength from the stress strain curve, first of all, that is defined with a sigma y, which is the yield strength, which we choose a deformation amount, which is 0.002. Okay, so choosing for all cases, basically for all materials, we choose the standard strain amount 0.002 and draw a parallel to the linear region, like a parallel linear region, and find its intersection with the stress strain curve, and then go to the y-axis to read the yield strength. Okay, this we do it for all materials, so we have a standard way of reading what is the yield strength. When we compare the yield strength of materials, this is gonna be for metals, against ceramics, graphite, polymers, composites. So for metals and alloys, we are seeing steel has a very high yield strength, titanium, etc. Of course, these are different type of alloys. These alloys can go through different type of heat treatments. For example, QT means for steel quench and tempered. So later we're gonna learn these heat treatments, because sometimes materials, to enhance their properties, has to go through certain heat treatments, meaning we increase the temperature, then suddenly quench meaning suddenly drop into water. And this causes, for example, small grains in steel. Therefore, the strength of the material is increasing, for example. Or different type of heat treatments can be given depending on these ladders we are seeing. Okay, and then right now you don't worry about these, because later we're gonna see how heat treatments can affect the strength of the material. And basically these treatments are changing the microstructure, grain size, and therefore of course changing the interaction of these grains with the dislocations, and therefore changing the strength of the material. You don't have to worry about that part. Right now we are just comparing the yield strength of materials within each other. So the ceramics are hard to measure, because they are not strong. Okay, they are stronger under compression. The very reason for that, the ceramics are susceptible to sudden fractures, and when we look at the failure chapter we're gonna see that. Okay, so because ceramics usually have pores and cracks inside them, and when we apply the tension, this crack can propagate, and then material can separate into two parts, basically suddenly fail. But under compression the crack doesn't propagate, because basically you are not pulling the crack apart, right? So that's why these materials are very good at under compression. Polymers have low strength values because the weak intermolecular bonds. Composites and fibers, this is also hard to measure, because again the fracture can occur before the yield. So we can only make logical comparison between metals and polymers, and we know metals are strong compared to polymers. So this is some data from virtual material science and engineering. I provided you to link, and go to that link, and depending on the alloy you choose, it will give you it's like a simulation of how the stress strain data is collected, and on the right, you can see how the material is changing dimensions depending on where you are at the stress strain curve. So I would suggest you guys to go to the link that I gave you and then observe some of these stress curves for different materials. So we learned about yield strength, right? It was the transition from the elastic to plastic deformation. And now we're going to learn about tensile strength, sometimes called ultimate tensile strength. And that is the maximum stress on engineering stress strain curve. So the stress strain curve we have learned so far, that is called engineering stress strain curve, because the force in force data is divided to original cross-sectional area, but in reality the cross-sectional area is changing throughout the test, but that doesn't include that information. Okay, so initially we start with application of the forces, then material elongates. This is the elastic region. We go to plastic region now, which is non-linear. The material starts to deform permanently, and at some point you reach a maximum. This maximum is where we reach the tensile strength. And then at certain point, when you reach that maximum, there is the thing called necking happens. That means the cross-sectional area of your specimen is now getting smaller. Okay, since now the cross-sectional area is getting smaller, the device has to apply less forces to achieve the same deformation rate. Remember, the device has to keep the deformation rate constant, but since it needs to apply less forces now, because the cross-sectional area is lowering, what happens when you put it into the engineering stress definition equation? It was force over original cross-sectional area. Since force is lowering because the device needs to apply less force now, the stress also lowering. So that's why we see when the necking starts, we see a decrease in the stress. Okay, until certain point, at certain deformation strain, and the material breaks. So we call that point is fracture strength. Okay. All right. This table again compares tensile strength. So if you look at the stress strain curve of each of these materials and choose the maximum point it reaches, and then read the strength value from the y-axis, that is going to give you the tensile strength. So it is not like yield strength where it is difficult to measure because there is a switch from elastic to plastic. Alright, so we see metals are the best, then ceramics, similar, then polymers come, and composites is a range, right? A wide range it covers because it's a mixture of different materials basically. So what is ductility? Ductility is basically how much you can strain, how much you can deform a material until it fails. So for example, if you think about rubber, you can keep stretching. It takes a long strain to be able to basically fail the material, right? So therefore it has high ductility. And some materials, even if you try to pull them and then try to stretch them, it doesn't happen, so they immediately break. like ceramics, for example. So they have low ductility. Okay, so this also affects how we can shape them. For example, copper is ductile and metals are ductile, and you can easily draw coppers into wires, but you cannot draw a ceramic into a wire because it doesn't flow, it doesn't have a ductility. So how do we measure this basically how do we measure this ductility? In two ways you can measure it. Percent elongation or percent reduction in the area. So very easy to understand, because how much you change the length basically gives you the ductility. So final length minus the original length over the original length times 100 to percent elongation. Or you can measure the same thing based on the area. Original cross-sectional area minus final cross-sectional area, because the original cross-sectional area is bigger than the final cross-sectional area, over original cross-sectional area times 100 is the percent reduction in the area. Both gives you idea about the ductility of material. You guys need to understand what I can ask in the exam is I can give you stress strain curves of different material, and I can tell you to compare them, like which is more ductile, which is more brittle, etc. So when you have low ductility, it's brittle because it immediately fractures after some strain. And some materials have high ductility. You can see it deforms to a large extent. Okay, so of course this is the plastic deformation, so it doesn't include the elastic recovery here. Alright, anyways, from looking at the x-axis and seeing how much it is strained, how much it is deformed, you can comment on looking at the stress strain curves. What is the ductility? Is it high? Is it low? Resilience is the material's ability to absorb elastic energy. Think about you wanna store elastic energy in the material. Okay, so think about it's a spring, you are stretching it, and as you stretched you are doing work on the material, because force times distance, right? These bonds are with applied force, they are stretched. So force times distance is work. Work is energy. Basically by stretching the material, you are storing energy inside those bonds, those springs in between the atoms, basically imaginary springs. That energy is recovered when we release the load. Okay, so what is resilience then? How we measure it? If we look at this under the stress strain curve and find the yield strength, and from the interaction of the yield strength line with the curve, okay, intersection of that line, you go down and find the yield strain. Okay, and that region is gonna give you the energy absorbed within the material. You can compare these areas of different stress strain curves and then comment this area is bigger in that material. That means it absorbs more energy. This energy or resilience is shown by modulus of resilience, U with a subscript R. This is the area under stress strain curve until yielding. So what does that mean? So area means integration, right? From 0 to yield strain, integrate stress strain curve, okay? So with infinitesimal changes of the yield strength, just integrate, take the sum up of all those little interactions, basically. So it will give you this equation. Integral means the area, right? So it will give you the area under the stress strain curve. If you assume it's completely linear change, okay, it's completely linear here, that means it's a triangle. So actually, if you want to find the area, you don't have to go through this integral. You can say it's a area of a triangle. So what I do, multiply y-axis to the x-axis and divide into 2. It's like area of a triangle. You can simplify it too. What is toughness? So resilience was energy absorption till within the elastic deformation region. Toughness is energy absorbed till fracture. So it includes all the areas under the stress strain curve. Okay, by definition, it is giving us units of energy per unit volume. So we look at, if we try to compare, the blue one is small toughness because the blue area is smaller compared to the green curve where the area under it is very large. But the pink one is also, even though it's very ductile, it has small area, meaning its energy absorption is small. Brittle materials have small toughnesses and it fractures immediately here, but the fracture it takes for this one to experience, it takes a long deformation, long energy absorption. So the ductile materials are generally have large toughness values, so you can correlate between ductile and brittle materials and to how much energy they will absorb. Okay. All right, as I explained to you guys, when we deform the material, things are moving inside with force, and basically we are doing work, and work and energy are the same. You guys know from other classes, right? So the work is equal to overall, if you sum up all these changes of length, right, with the force, it will give you the work or the energy stored inside the material. So what about work per or energy per volume, right? We're gonna divide then to volume, which is area times length. And this will tell you force over area is stress, dl over L is the deformation strain. So therefore, by definition, the energy absorbed per volume is the area under stress strain curve. And this is giving us the toughness, the energy absorption capability of a material. And in some application, you want the material to tough. You want it to absorb as much as energy possible before it fails. Such as a car bumper, for example, right? It should absorb all the impact energy. Now, I told you there is, so far we have learned engineering stress strain curve, because I told you the engineering stress strain curve uses original cross-sectional area to calculate the stress in the diagram. That's why it is decreasing, because when the force is decreasing, the area is the same, the stress is decreasing in the curve. However, in reality, it is always increasing, because the area is actually not constant like taken in this equation. It is actually decreasing too. So it is decreasing to larger extent compared to the decrease of the force. Therefore, stress is increasing actually in reality. Okay. So we can see that area is changing, right? It is like this. especially after this reaching maximum where the necking starts, the area is getting smaller. So that is called true stress strain, and the equations are different. To measure this true stress, you divide it to each time the instantaneous cross-sectional area. For the strain, it is given with this equation. Okay, so Li is again the instantaneous length. There is a relationship that relates engineering stress to true stress strain, and these equations are given here, and these are valid only after the necking. So why we don't usually collect true stress strain data is because it doesn't matter. Because why? Because what matters is that the yield strength, as I told you many times in the design, yield strength or ultimate tensile strength, these are the ones that are important, and up to that point both curve gives us a similar result. And the reason is, once the material deforms plastically, it doesn't serve us the purpose of our using it in that application. So that's why engineering stress strain curves are enough, but in reality true stress strain curves are the real ones, basically, because the lengths and cross-sectional areas are different in a given time. So between the point of yielding and the onset of necking, alloys are described through this equation. So if we look at the yielding starts here to the necking here, right? From this point to that point, this line, okay? This line is described the relationship between the stress and the strain. Actually, this is for the true stress strain curve. Is described with this equation. How with stress the strain is changing, and there is a power n, and then there is a constant k, and n and k are constant that depends on the material, basically. Okay, and it is basically what we call n is as strain hardening exponent. Well, later we're gonna see in this region actually what happens as we deform the material plastically. It is getting more stronger and stronger, and we're gonna see why that is in the later chapters. And strain hardening, basically hardening means strengthening. With strain the material is getting stronger, so that region, the power n, is called strain hardening exponent, and it tells us the information that how effective basically the deformation in strengthening that material. So we are seeing true stress strain curve, and how materials with small n behaves like, and with larger n behaves like. So if the n is larger, that means it is the strengthening is taking place more effectively as we deform the material. So as we talked that elastic strain in the deformed part is recoverable, and that graph is demonstrating that. So you deform the material up until point D, collect stress strain data, okay, and once that happens you remove the stresses, and materials, the elastic region recovers, go back to original go back to recovering the elastic strain. what happens? This much plastic deformation remains, but this much elastic is recovered, and I explained to you guys that if you actually repeat the same experiment in the same material, you apply again, let's choose a color here. If you apply again another stress, again elastic deformation, this time the yield strength will be higher and keeps deforming plastically. The reason is, once you deform the material right there plastically, the strength of the material increases. That's why deforming materials actually increases their strength. They call this cold working. At room temperatures, they work on the material, like they extrude them or roll them, or do forging, like hammering. These things, these cold working on the sample actually increases the strength. So once you deform the material, it is getting stronger. That is the thing you want to keep in mind. So if you deform a material, it gets stronger. So think about a paper clip, and you keep deforming them, deforming it, keep deforming it. At some point it's gonna get difficult to deform, because as you keep trying to bend it, you are working on the material and you are deforming plastically, and the material is getting stronger as you keep trying to bend it. What happens is, material actually is getting difficult to deform because it is getting stronger. So what is hardness? It is again another mechanical property of the materials. So it is the measure of resistance to surface plastic deformation, or measure of resistance of the surface to dent or scratched. It is something that is very related to the strength of the material. So usually strength and hardness are correlated. Okay. So large hardness means the material surface will resist to deformation from compressive loads, and it will have better wear properties. So if a material is hard, that means it's have better wear properties. So how it is measured? There are different hardness tests, and one of them, how the experiment is done, how our hardness is measured, is in the videos I sent you guys. I suggest you to watch them to learn how hardness is measured. So there is an indenter that can be made out of steel or other alloys, hard material, that is pressed by force into the sample. So this is your sample here. Okay, you have an indenter which you press on the material, and then you measure the diameter of that indentation, okay, after you unload it. So that diameter will gonna tell you about what is the hardness value of that material. So diamond is the hardest ones, and then comes nitride steels, cutting tools, and another type of metals and alloys. But plastics are in the lowest scale, so they are not hard. But the diamond is the hardest material. Okay. So as I said, there are different types of hardness tests, depending on what type of indenter they use. So what is the shape of the indenter? What type of loads they apply to? Based on that, people came up with hardness tests. One of them is called Rockwell hardness. And for Rockwell hardness, we have a diamond indenter or steel, and then the loads that are applied are in this range. And based on that, basically we measure the hardness, and we correlate that diameter measured to a hardness value. In reality, this hardness value is not exactly a representation of what is the hardness. That doesn't have a meaning. The hardness value is. It is just made up equation to relate between the measured indentation parameters to a hardness value. That's why all the different types of hardness tests are using different equations to obtain a hardness number. So you just call it a number. How they figure out how it's related to the strength is they collect data basically as a function of this hardness number. What is the actual tensile strength, let's say, and then from that data now, if you collect a diagram, each time you measure the hardness from that diagram, you can go ahead, let's say strength hardness number. Okay, so you collected a data, let's say the relationship was like that. So each time you measure the hardness, you can correlate it to the strength. So like a calibration curve, you first collect that, and then with the given hardness number, you go ahead and just read the strength. This is how you can relate it. So designation in the Rockwell hardness HR, just for the Rockwell hardness. And then some other information is given, some examples, and the range of the Rockwell hardness test. Another one is Brinell hardness test. That one is in the video that I provided you guys. At this point, it's here as I explained, the hardness number, how it is measured. HP is the Brinell hardness. This one uses a sphere of tungsten or tungsten carbide and or a steel indenter to push on the material. And the D, capital D, is basically the diameter of that sphere. It is 10 millimeter, and D is the indentation diameter. That's why if you plug in these numbers in these equations, again this equation is different for each different types of tests. For Brinell hardness, you use that equation to calculate the hardness number, and we are given the range of loads that are applied, and there also has been found a relationship between the tensile strength and calculated Brinell hardness values, and these equations are given here depending on which units you want to use. If you're going to use PSI or megapascal, depending on that, you just have to multiply the Brinell hardness to certain number and you calculate the tensile strength. Okay, so this relationship is important. Alright, so the problem arises when we do testing, because even we are sampling the same material, each test will not gonna give us the same result. Okay, there will be small variations between the results of the test, even for the same material. Therefore, we need to approach the problems with some statistical treatments. How do we take the average value? Let's say, how do you measure the yield strength? If the test gave you multiple yield strength for the same material, how are you going to get that yield strength? You need to average it, right? N being the number of measurements, xi being the specific measured value, just average them. And also standard deviations, how the data is scattered, how much it's scattered. Let's say this is the average and the data is scattered everywhere, right? So how much it scatters. Basically, this is the basically you basically need to square it, because what are the distances to the mean value, right? So basically average value, this is the average value, remember. So each data, how it is changing relative to the average value. That can be a negative change or positive change. Therefore, we need to square it to get rid of that negativity, and then do square root of the overall, and then divide it to basically how n minus 1. Okay, you start from 1 and then do the an experiment n times, right? So that's it basically. So there are some safety factors because there can be uncertainties. And we need to protect to make sure there is not going to be a failure. At least make sure of it. I mean, at least try our best, right? So for structural applications, to protect against the failure, use working stress sigma W and the safety factor. So the safety factor relates the working stress to the yield strength of the material. And the yield strength, of course, needs to be bigger than the working stress, because this will ensure that the possibility of failure will decrease. So here is an example. We have a cylindrical rod and constructed from steel, and the steel's yield strength is 310 megapascal. Is to withstand it will withstand a load of force of 220,000 Newton without yielding. Okay, assume a value of 4 for the safety factor n, and specify a suitable bar diameter. Okay, so this material is going to be exposed to loads, the force of 220,000 with a certain area, right? And that is the working load, working stress. And the yield strength of the material is 310. So this is given to us. We plug into the data, the equation, and n is assumed to be 4. From that you can calculate, because the working stress is the force over area basically, and area is diameter over 2 is the radius squared, right? Pi r squared, pi d over 2 squared. So this is the area and this is the force. And from this equation you can calculate the diameter that this steel bar needs to be constructed from. Okay, so basically you are ensuring that the working yield strength of the material is 4 times of that working stresses. You will try to lower the possibility of failure with this safety factor. That's it. So in summary, we looked at how the materials are reacting to mechanical forces and how much they deforming. We said it's giving us stress and strain data. And elastic deformation is non-permanent, occurs at low stresses, it's linear. Plastic deformation occurs at higher stresses, it's non-linear. Stiffness is a property of material due to the atomic bonding strength. It is determining the resistance to elastic deformation. If the material is difficult to deform elastically, we call it stiff, and try to deform a steel bar, for example, with your bare hands, right? It's difficult. But try to deform a material with low modulus like a rubber, you can easily deform it elastically. So strength was 2 types, yield and tensile strengths. It was the material's resistance to plastic deformation. Ductility is how much we can deform the material, to what extent until it fails. So we calculated from percent elongation or a reduction in the area. Hardness is resistance to scratches, the surface deformations, and under compressive stress. And this is measured with a lot of different hardness tests available. If you look at your books, it gives you all of them, and you can correlate those to each other. But in the end, the famous ones are Rockwell and Brinell hardness. And again, I suggest you guys, I provided you videos how the tension test is done. There are animations how the hardness tests are done, and I suggest you guys to watch those videos to get more visual information about what I'm trying to tell here. Normally, because in the lectures I was able to show those videos to you, but now I want you to guys watch them yourselves, okay? So take care, and then I'm gonna talk to you again next time, this Wednesday. Okay, see you guys.